I'm going to present the ODOS, that's the solution for OpenMP DPU offloading support that we've developed. And yeah, just a quick recall what DPU, particularly what the NVIDIA Bluefield DPU. That's a high-speed NIC with some specific offloading hardware and general purpose CPUs. So we understand that the smart NICs in HPC can be leveraged in order to overlap computational stages. Particularly, we've detected three interesting cases that are pre and post-processing in order to compress the compressed data, pack and pack, or cipher decipher. Also, we can use it for asynchronous or independent tasks when storing and loading data, checksum or validation, or data augmentation stages. And finally, we can overlap computation and communication in algorithms as adaptive mesh refinement, neighbor building, or Halo exchange. Particularly, I'm going to use Halo exchange in order to illustrate all the work we've done. As well described by Moritz and Jeff, the Halo exchange, we have different subdomains spread among different processes, and we've defined these stages to understand these areas to understand better what's going on. So we have the inner subdomain that is the massively parallel part, the outer subdomain that it's at the extremes of the subdomain, and a Halo area that's the exchange area. So really quick, we have two nodes and two subdomains. So the Halo exchange is sending the outer subdomain to the Halo of the neighbor. And now we'll see the Halo exchange of loading. So for this case, I like to introduce a setup based on two nodes. Each node equipped with a GPU and a smart NIC. So in the first iteration, we are going to process the subdomain, and while the GPU is executing the inner subdomain, we have the smart NIC processing the outer subdomain and communicating. So at the end of the iteration, we will have we have the state updated, and we can continue with the second iteration. And the second iteration will do the same. The smart NIC compute and exchange while the GPU is executing the inner subdomain. So as you can notice here, we are having the Halo exchange stage for free. Now let's see how can we code this. One option is using low-level APIs, particularly the NVIDIA Bluefield DPU. We have a Docker SDK. To understand us, it's like Docker is to DPUs what CUDA is to GPUs. However, we consider that this is too low level for the main scientists. This is a complex SDK. Another alternative is the NPMD execution model, the multiple program, multiple data in MPI. Here we have different kind of processors, and we just need to decide what data is going to be in each one. The cons here is that the poor productivity when coding it because of the wildly different processors. Let's see an example of an MPI code here. What we want to do here is just executing this loop in the smart NIC. So first we have to move data from host to DPU using the discriminating among ranks. So the DPU rank will receive the data. Once the data is there, we can run the loop itself. And when it finishes, we will send back the data to the host. So this is a spaghetti code because we have to discriminate each rank what has to do. So if we want something more compact, more lasagna code, we could use OpenMP. OpenMP, particularly the syntax provided by the PragmaOMP target. In this case, we just need to define the data to offload, and everything in the pragma will be offloaded to the SmartNIC. But some of you can be wondering, okay, yeah, this is for GPUs, but there is no implementation for SmartNICs until now. Okay, so now we are presenting here ODOS, that is OpenMP DPU offloading support. And thanks to it, we can do what we do with kernel offloading to GPUs, but also for SmartNICs DPUs right now. The basic syntax, the same. We are compliant to the OpenMP standard, so everything within the bracket will be executed in the DPU. And if we have more devices in the same host, there's no problem. We just need to run LLVM OMP device info, and in this case we have a V100 with the ID4, but in the ID7 we have a Bluefield DPU. So as easy as just determining the device where we will offload the code. The ODOS architecture is based on a client-server scheme. So we will have a service running on the DPU, the Docker OMP service. And when the user initiates its program, his binary, the LLVM OpenMP runtime on the host will communicate with the service using the Docker secure communication channel. ODOS is composed of 3 modules, 2 in the host and 1 in the DPU. So the first one is the cross-compilation module that, for instance, Bluefield DPU, they are equipped with ARM processors. So in the case of the host, it's a different architecture. We just need to cross-compile the binary. And both binaries are grouped in a fat binary. The target plugin, the OpenMP target plugin, is responsible for communicating with the service in the host, in the DPU, sorry. And it will send the command to load the binary, to allocate and exchange data, and executing the kernel itself. Those commands are received by the Docker OpenMP service, and when it receives a load binary command, it will save the image as a shared object. It will open the image and then send back the handles of the symbols of that image. If it receives a data operation command, it can be allocate, delete memory, send or retrieve data. And finally, when it receives the target block execution command, it will use the handles of the image to run that kernel with the given data. So in this sense, the ODOS flow, we are using DPUs as an accelerator instead of a co-host. So DPUs becomes very friendly to use for the HPC user, much more if they are familiar with OpenMP. So the flow is, okay, we start, the host sends data to the DPU, sends the binary to the DPU, then the DPU runs the binary with the given data and sends back the result to the host. Let's see a few programmatic examples. The basic one is just printing a message. We are printing a message in parallel. Okay, so for that, we will execute the service in the DPU and we will run the binary from the host. So the result is 16 messages printed in the service because we've offloaded this parallel kernel. The second example is an asynchronous TCP communication in which we are going to offload the TCP initialization and also a ping-pong function. So when the service receives this kernel, the host offload the kernel to the DPU. So now the service receives the kernel, and this action is this function. And when we run the second function, depending on if we are in the client or the server, we will ping or we will pong. A major milestone in ODOS recently presented is the support for MPI offloading. So, as we've been seeing here, we can offload also MPI operations. The first example here, it's a point-to-point communication in which rank 0 sends data from the host, from the DPU, and it receives data. Rank 1 receives the data in the DPU because we've offloaded that kernel to the DPUs. The second example is a collective communication where all the smart NICs execute the all-to-all operation. Okay, so now let's come back to the Halo Exchange offloading, and we can see here how we are going to implement it. Just to remember what we will see is that we have two nodes, GPU and DPU per node, and exchanging the outer domain with the halo of the neighbors. And this is the code. Don't be afraid because it's pretty easy. We have two really, we easily to differentiate stages. One is the GPU offloading and the other is the DPU offloading. So those are executed asynchronously, and we will wait at the end to synchronize both for the next iteration. The DPU offloading. Okay, we map here the inner subdomain, the massively parallel area. We define the device that it's the GPU ID and executed it asynchronously. So we can use the traditional prime OMP clauses for GPUs, and we will offload this kernel, the inner computation. For the DPU case, what we have, we're going to map the outer subdomain, in this case left and right, because we are having neighbors left and right, and define the device ID and also asynchronously execution. In this case, we are using the clauses for SIMD because of the architecture we have in the DPU. And for left and right, we are creating two tasks for the outer subdomain. And this particular function, what does is the compute of the outer subdomain, that it's compared to the inner subdomain, it's really small, and the asynchronous communication for the Halo Exchange. Okay, and now just to finishing some performance numbers, particularly using this testbed for nodes of HPC AI Advisory Council, in which we have a Bluefield 3 in each one. And for the software stack, we're going to evaluate the OSU micro benchmark and the mini weather application. The first test is here we have the latency of the point-to-point communication for the four different modes that ODOS allows, that it's host to host, host to DPU, DPU to host, and DPU to DPU. We can see that as the message size increases, the latency converges. But for small and for medium sizes, we see that the DPU to DPU communication, the latency is lower. And that makes sense because we are closer to the network. So if we change one DPU by a host, the latency increases a bit. And when we use both hosts, the latency is the highest here. Okay? That's for point-to-point. Now for one-sided communications. The same four modes. Here we have a different behavior, and that I'm going to explain. We see that for small and medium messages, we have lower latencies when the communication is started from the device. But when the message size increases, the latency is lower when the communication is started in the host. And that makes sense because This is a get operation, one-sided. So the remote memory is already allocated, but the local is not allocated until the operation is started. So in that case, for larger messages, the compute capabilities makes a lot of sense. And that's why running that in the hosts are more powerful, and we can have lower latency. The collective, for instance, this one, the asynchronous all-to-all, we are comparing here ODOS MPI with against vanilla MPI or OpenMPI implementation. And we can see that for all message sizes, ODOS MPI performs better, and that's mainly because we have an extra coprocessor helping us to do that operation. So we can overlap above 94% the operation. So we can overlap the communication and computation of this all-to-all. The second application I will describe is mini weather. Mini weather is just an application that mimics the atmosphere, the dynamics of atmosphere and climate. So in this case, we've refactored this application to implement the Halo exchange offloading. Particularly, as you can see here, we have an inner subdomain and two outer subdomain corresponding to the neighbors that we have. Of course, we can define the thickness of the outer subdomain depending to balance that computation. And that's what we have here in this result. We have in the x-axis the problem size, the y-axis is the speed up, and the bars, the color bars, is the ratio of the state offloaded to the DPU. In other words, the thickness of the outer subdomain. So depending on the configuration, we can see that we can obtain up to an 18% of speed up that corresponds to this case, balancing the data in the SmartNIC and in the host. Okay, so just wrapping up. In conclusions, we have the SmartNICs in HPC are highly promising. We saw that at the end of the day, we are having an extra coprocessor closer to the network, so we can use it. Applications can be accelerated, among others, by overlapping and offloading communication. And we consider that the easy coding is crucial to extend SmartNICs usage among HPC users. So thank you.
All right, yeah. Thank you. Do we have any questions?
Thank you. Regarding the last result that you presented with data ratio of state in DPU, can you elaborate what exactly that means?
Yeah, it's the percentage of the subdomain offloaded to the DPU. In this case, is this part. Okay, we have a subdomain of okay, this is a subdomain of 1K of cells, and we are offloading a 32% to the DPU.
You mean so it's originally stored on the DPU and the computations are also done on the DPU?
It's particularly this amount of data. We map that part of the array to offload it to the DPU.
Okay, I understand, but only for Halo exchange or also for compute?
Well, depending on the thickness of that halo, we will compute more or less. So yeah, we are computing more than exchanging. That's your question, I guess.
Yeah, okay, thank you.
Because what we're trying to do is to balance the time spent in computing the inner subdomain with the outer subdomain. So if the communication is fast enough, we can give more load to the SmartNIC. to compute it and try to balance. At the end of the day, what we want is to have that computation for free and that communication.
Any other question?
Yeah. So thanks for the talk. So for that meeting weather, so how did you, I guess, the follow on Mark's question? So how was the load balance determined?
Experimentally.
Okay.
So we try different percentage of the thickness, and these are the results that we try. So until we get we got the maximum, we stop trying sizes.
So for any other application I would have to very carefully tune it.
Exactly.
For everyone.
And it depends on your hardware setup and all that stuff. Yeah.
No, thank you.
You're welcome.
Any other question? I have one.
Yeah.
So in Morit's talk, we heard about like different GPUs behave differently when it comes to floating point rounding and stuff like that. Do you see similar things with the DPU compared to the CPU or compared to the GPU that you're using?
That's a good question. Since we are cross-compiling, probably there are some discrepancies, but they are not appreciable in the results.
They don't flash out, so to say, they don't have an impact on your computation.
We didn't. Yeah, we checked the results were correct.
Okay.
Thank you for the talk. I have a question regarding the latency chart that you showed. At some point, latency increases with the message size. You said that it is because on the target device, the memory has to be allocated first. Why is the memory not allocated like the entire time on the target side and like only the data transferred, which would keep the latency the same?
Okay, we've tried to follow the OpenMP and MPI syntax and standard, so we didn't change anything from there, and that's how one-sided communication works. So yeah, that could be an optimization, but we try to be totally compliant with the standards.
Thank you.
Thank you.
Okay, so if we do not have any other question, then thanks our speaker
Thank you.
again.
Thank you.
Very much.
Before leaving, just some spam. There is a deadline at the end of the month for the special issue in the future generation computer system. And if you want to collaborate with us or just visit Barcelona, we are organizing a hackathon in October. Thank you.